In our intuition, time is an abstract concept that exists independently. It has only one direction, steadily flowing from the past to the future. But have you ever wondered why this is so? Why can time only move forward and not backward? Why is it that we can remember the past but not the future? Do we exist within time, or does time exist within us? Today we'll be discussing the book The Order of Time. This book will take us on a journey to explore the nature of time, challenging our conventional understanding of it. The author of this book, Carlo Rovelli, is an Italian physicist and one of the pioneers of loop quantum gravity theory. He is often hailed as the next Stephen Hawking. The Order of Time is Rovelli's latest work, which was named one of the top 10 non-fiction books of 2018 by Time magazine. The audiobook of this book, narrated by Benedict Cumberbatch, who plays Doctor Strange in the Marvel films, won the British National Book Award. We will explore this book in 3 parts. First, we will examine the truth about time from both macroscopic and microscopic perspectives. Second, we'll enter a world without time and see how things would operate without its guidance. Third, we will explore why, even in a world where time does not exist, we can still feel time so vividly. Let's begin our journey to uncover the truth about time. The truth about time, macroscopic and microscopic perspectives. First, let's take a fresh look at time and search for its true nature. From a macroscopic perspective, our most immediate perception of time is that it has 4 main characteristics: independence, unity, presentness, and directionality. Time seems to exist as a separate entity, moving consistently in one direction, from past to future, and always in the present moment. However, recent developments in physics have upended these traditional views. The independence of time. Let's begin by discussing the independence of time. People generally believe that time operates independently and that no force can stop it. This viewpoint originated with Newton. Newton believed that time is absolutely independent and has no connection to external events. This concept of time formed the foundation of modern physics, and today we consider it a given. However, time's independence is just Newton's personal perspective. It is not an innate intuition of humankind, and some philosophers have opposed it. One such philosopher was Aristotle, the first known individual to ask, "What is time?" His inquiry predates Newton by nearly 2,000 years. Aristotle believed that time is a measure of change. In other words, when we talk about time, we're actually talking about things that change. For example, when I say, "I will be away for 3 days," those 3 days refer to the time it takes for the sun to complete 3 cycles across the sky while I am gone. It's as simple as that. So if nothing changes, does time stop? Aristotle's answer would be yes. If everything were to remain unchanged, time would cease to exist because time is merely a record of change. But then, why is it that even when we lie still in the dark of night with our eyes closed, we still feel time passing in the silence? That's because our minds are not still, our thoughts change, and that's why we still feel time moving. This view, which holds that time must be tied to change, is the opposite of Newton's. A contemporary of Newton, the German mathematician Leibniz, also opposed the idea of time as independent. He argued that time cannot exist on its own. Behind it lies something more fundamental: causality. For example, imagine there is a beer mug on a table. There are many causal relationships hidden within this scene. If the beer cap is not removed, the beer cannot be poured. If the beer is not poured, the glass will not be filled. By understanding the causal relationships, we can understand the sequence of events over time. To Leibniz, time is like a domino effect, a continuous transfer of causal relationships. The first domino falls, affecting the second, which in turn affects the third, and so on. When we experience this transfer of causality, we also experience the passage of time. Leibniz strongly defended this view of time. Legend has it that his name originally had a T. In Newtonian physics, T stands for time. Leibniz, who believed that Newton's absolute time did not exist, removed the T from his name to align with his belief. So, is time independent? Einstein made the final judgment. Time does not exist independently. Let's look at how Einstein proved this. First, he established the principle that the speed of light is constant. That means the speed of light is the same for all observers, whether they are stationary or in motion, whether on Earth or in a spaceship. According to special relativity, traveling faster than light is impossible, which indirectly supports Leibniz's view. Why? Imagine someone sends you a superluminal message. You would receive the message before even seeing the sender take out their phone. This would break the chain of causality. Allowing faster-than-light phenomena would lead to absurd scenarios, a glass breaking before it hits the floor, or seeing a victim dead before the killer pulls the trigger. For this reason, Einstein's special relativity established the invariance of the speed of light. This setting ensures that all causal relationships are preserved, indirectly supporting Leibniz's concept of time. Second, Einstein proposed a new view of space-time. Earlier, we discussed that the speed of light is constant and that space is vast. Light takes time to travel from one point to another. The greater the distance, the greater the time gap. Hence, time and space are inextricably linked, inseparable. A good example is the use of light years to measure space. It's essentially using a time concept to describe distance, indicating that time and space cannot be separated. Einstein unified space and time into one entity, space-time. He didn't just unify time and space, but also gravity. For example, the sun's gravity causes Earth to orbit. This is because the sun's massive mass curves the surrounding space, and Earth simply follows the curved space. This curvature of space plays the role of a gravitational field. Since space and time are one, space-time is a gravitational field, and a gravitational field is space-time. A field is a physical entity, just like electromagnetic fields. Gravitational fields are not detached from us. They are dynamic and linked to the changes in the world. In Newton's view, time is like a stage, with life and matter on the stage as performers. No matter what the performers do, the stage time remains unchanged. However, in Einstein's view, the stage changes as the performers perform. Time no longer has absolute independence. The unity of time. Now, let's discuss the second characteristic of time, unity. People generally believe that time has unity, meaning that time treats everyone equally. Time is perceived as moving at a constant, uniform rate by everyone around the world. However, the reality is quite the opposite. Time is never fair. Its true nature is that it speeds up and slows down unpredictably. Two factors influence how time flows, mass and speed. First, let's talk about mass. Objects with mass cause time to slow down around them. The greater the mass of the object, the more pronounced this slowing effect becomes. This is because the gravitational pull of large masses distorts the space-time around them, and the larger the mass, the greater the distortion. Take the Earth, for example. The closer you are to its center, the slower time passes. This means that people living at sea level age a little slower than those living on mountaintops, even if the difference is just a few centimeters in altitude. This fascinating effect exists even in such small variations. In other words, cells at the feet of a person age more slowly than those at their head. Now let's talk about speed. Moving also makes time slow down. The time inside a high-speed train moves slower than the time on a bicycle. The faster you go, the slower time moves for you. But why is that? Let's conduct an experiment. Imagine a photon clock, a simple device with two mirrors facing each other. A photon bounces vertically between these mirrors, and its back and forth motion is used to measure time. On the ground, if the mirrors are 1 meter apart, the photon will complete nearly 150 million trips between them in 1 second. Now, let's place this clock on a spaceship moving at high speed. What happens? The person inside the spaceship sees the photon moving vertically, but for you, observing from outside the spaceship, the situation looks entirely different. While the photon is moving up and down, the spaceship is moving forward. This combination of motions makes the photon appear to be moving diagonally. In other words, the distance the photon travels appears longer. Since the speed of light is constant, the time it takes for the photon to make a round trip also increases. Therefore, from your perspective, time aboard the spaceship has slowed down. Everything seems to unfold in slow motion. If someone aboard the spaceship sneezes, it might only take a second for them, but from your point of view, it seems like a minute has passed. We now understand that time can be altered by mass and speed. People at different altitudes or in different modes of transport experience time differently. So, which version of time is the real one? The book points out that since many different versions of time exist, none is more real than the others. Thus, we have overturned the second characteristic of time, its unity. The presentness of time. If two people experience time differently, how can they communicate with each other? Let's explore the third characteristic of time, its presentness. An important concept in time is the now. If your family member is in the room and you want to know what they're doing, you can just look and know. However, you need to be aware that the image you are seeing is light that has traveled from them to your eyes. Light takes time to reach you, usually just a few nanoseconds, 1/1000th of a second. So you aren't seeing what they are doing right now, but rather what they did a few nanoseconds ago. This is such a short time that we usually ignore it. But what if your family member lived 4 light years away on Proxima b? The light would take 4 years to reach you, so you'd only see what they did 4 years ago, not what they're doing now. You might say, but in 4 years, when I see them doing something, isn't that the same as what they're doing right now? Unfortunately, this doesn't work either. As mentioned earlier, time in the universe is not uniform. Although 4 years may have passed on Earth, on Proxima b, it could have been 10 or 15 years in their time. Moreover, asking which moment on Proxima b corresponds to now on Earth is nonsensical. It's like asking which team won the basketball championship or which person became the US president. There's no corresponding moment on Proxima b that aligns with Earth's present moment. Not just on Proxima b, but in the entire universe, there is no universal time. Time concepts are localized. The now on Earth is like a bubble around us. It's always just our present, not extending across the universe. How far does this bubble stretch? It depends on the precision with which we measure time. The higher the precision, the smaller the bubble. If we measure in nanoseconds, now extends just a few meters. If we use milliseconds, the range expands to thousands of kilometers. Since humans have difficulty distinguishing fractions of a second, we consider the entire Earth as part of the same bubble. So our definition of now is a fuzzy description based on our perspective. It's like seeing a rainbow meet a forest in the distance. We think we can see it, but when we approach, it's not there. For our daily life, these differences don't have a huge impact. The directionality of time, past to future. Time, with all its nuances, presents us with its most unforgiving and relentless feature, directionality. For centuries, people have lamented that time never returns, that once it passes, it's gone forever. So why can time distinguish between the past and the future? This question has been at the heart of 19th and 20th century physics. Although we feel that time flows steadily from the past to the future, finding a law or equation to distinguish the past from the future has proven to be almost impossible. Whether it's Newtonian mechanics, Maxwell's electromagnetism, Einstein's theory of relativity, or Heisenberg and Schrödinger's quantum mechanics, all these physical equations describe phenomena that are reversible. In simpler terms, if an event happens in one direction, these laws allow it to happen in reverse as well. For instance, if you know the position and speed of a planet in the future, you can calculate its past position and speed just as easily. So if both the forward and reverse directions are possible, how do we justify calling one direction past and the other future? The only irreversible law in physics is the second law of thermodynamics. This law states that heat flows from a hotter body to a cooler one and cannot reverse. This is the only law in physics that distinguishes past from future, and it's deeply connected to the directionality of time. Everything that makes the past and future different involves heat. When a stone falls to the ground, mechanical energy is converted into heat, slightly warming the stone and dispersing energy into the surroundings, thus stopping its motion. Without the involvement of heat, the stone would keep bouncing forever due to the conservation of energy. Life ages because of the heat produced by biological processes. Bicycles wear out due to friction, and even our brains heat up as we think. The passage of time is always tied to the generation or movement of heat. Heat, as the only physical variable linked to irreversible phenomena, also plays a role in marking time's direction. Now, how does heat help distinguish between past and future? If the universe were in a state of thermal equilibrium, where temperatures were the same everywhere, there would be no change and consequently no passage of time. This is something that we can only answer by looking at ourselves. Our perception of the world is blurry and incomplete. Let's take a simple example. Imagine a deck of cards with 26 red cards followed by 26 black ones. We call this arrangement ordered. Now, if you shuffle the cards, they will no longer have the same distinct order. Each arrangement, no matter how random, is unique in some way, but it only becomes ordered when we focus on certain aspects, like the colour. Similarly, when we look at the universe, we see it as a massive deck of cards. Our planet, though small, interacts with a tiny fraction of the cosmic deck, and we cannot see or understand all of its configurations. As a result, we imagine time as flowing from the past to the future, giving us the illusion of order. If we could consider the entire universe's details, no arrangement would be more ordered than another. And this leads us to the idea that time's flow, the feature that separates the past from the future, might only be a product of our human perspective. This realization comes with a startling conclusion. Time's flow may not be a fundamental feature of the universe at all, but rather a unique viewpoint created by human perception. In the macro world, time loses its independence, unity, presentness, and directionality. Time as we know it starts to lose all its familiar characteristics. In the microscopic quantum world, time's continuity and determinism, commonly accepted in everyday life, also face disruption. In quantum mechanics, time behaves differently than in classical physics. It is not continuous. Instead, it operates on a quantum scale, revealing a surprising and often perplexing view of reality. An important aspect of quantum mechanics is its uncertainty principle, which states that we cannot determine the exact position of a particle. The particle is in a superposition of states until it's measured. This is famously illustrated by Schrödinger's cat, a thought experiment that shows how quantum superposition works. In this experiment, a cat is placed in a sealed box with a small amount of radium and cyanide. The radium has a chance of decaying, triggering a mechanism that breaks the cyanide bottle, killing the cat. If the radium doesn't decay, the cat survives. According to quantum theory, since the radium is in a superposition of decayed and undecayed states, the cat is also in a superposition of being both dead and alive until observed. This paradox is called Schrödinger's cat. When time itself is in a superposition, an event can exist simultaneously in both the past and the future. It's hard to imagine, but this is how the quantum world operates. So, after analysing both the macro and quantum worlds, we see that time has lost many of its traditional characteristics. The familiar time we know is almost unrecognisable. A universe without time. So how would the world operate without the guidance of time? Let's move on to the second part of our discussion and explore how a world without time would function. In 1967, two American physicists discovered a fundamental equation for quantum gravity, and remarkably, this equation didn't include time as a variable. Time had disappeared. At first, no one could understand the equation, not even the physicists who discovered it. Without time, does the world come to a standstill? But later, people realized that the disappearance of time from the equation didn't mean that everything would freeze. On the contrary, it meant that change would be ubiquitous, occurring without the need for time to direct it. What the equation described wasn't how things change over time, but rather how things change relative to one another. Let me give you an example to clarify this. Galileo discovered that the pulse of the human heartbeat could be used to measure the time it takes for a chandelier to swing. Later, people realized that because the time it takes for the chandelier to swing is consistent, they invented the pendulum. Doctors began using pendulums to measure a patient's pulse. Notice the cycle here. Galileo used the pulse to measure the pendulum's swing, and doctors used the pendulum to measure the pulse. In reality, time is just an intermediary. We don't actually measure time itself. We measure the pulse and the pendulum, and then we observe how these two physical quantities change relative to each other. So-called time is like an auxiliary line we draw in geometry problems. This line doesn't exist, but it helps us solve the problem. If we can find synchronized variables, like the pendulum and the pulse, we can use their mutual changes to represent time, without needing to pick out one variable and call it time. When we discard time, one thing becomes clear: the universe is made of changing events. We once thought the universe was made up of objects, but in reality, all objects are just events in flux. For example, a rock isn't just an object, it's a complex vibration of the quantum field. A cloud isn't just an object, it's the condensation of water vapor in the air. A family isn't an object, it's a collection of relational events and experiences. A person isn't just an object, they are a complex process involving food, information, language, and more. In this universe made up of changing events, everything could play the role of time. This is how the real world functions. But here's the big question. If the world doesn't have time, then why do we experience time so vividly? Where does it come from? Where does time come from? Let's move on to the third part of our discussion. Where does time come from? Time originates from our memory. Earlier, we mentioned that heat plays the role of time, and it leads to an important result. It leaves traces. For example, when we write, the friction of the pen heats the paper slightly, leaving a mark. We judge time by these traces. What has a trace is considered the past, and what doesn't have a trace is considered the future. In a world without heat, a pen cannot leave a mark on paper, and we wouldn't be able to judge time. Our brains can collect traces from the past and form memories from them. Additionally, our brains can combine scattered memories to predict the future. For instance, when someone throws something to you, your hand will skillfully move to catch it at the spot where it is about to appear. This is the brain using past impressions to make a judgment. The brain also tells us that planting seeds will yield food, and going out in the rain will get us wet. When we see a cup fall to the ground and shatter, our brain does not create three separate signals, but instead creates a single signal representing the entire event. We perceive the entire process of the event, not isolated moments. It's like listening to music. We hear the relationship between the notes, not individual notes in isolation. If the brain couldn't connect them, we couldn't enjoy the beautiful music we hear. So the time we experience is a continuous feeling created by our brains. This idea is quite ancient. The Roman philosopher Augustine questioned the nature of time in his Confessions. He said that when we measure time, we are measuring something in our minds in the present. Time, he argued, exists within us. German philosophers like Kant and Heidegger shared a similar view, believing that time exists only in the human realm, shaped by our inner perceptions. Writer Marcel Proust delved deeper. In the first volume of In Search of Lost Time, he wrote that reality is made entirely of memory, and so we've come to understand the truth about time. The truth about time. Let's go over the 6 commonly believed characteristics of time. None of them actually exist. 1. Time is not independent. It is linked to the changes in things. 2. The speed of time can be altered by mass and velocity. People at different altitudes or using different modes of transportation experience time differently. 3. Time doesn't have presentness. What we consider now could be the past or future for someone else. 4. The flow of time from the past to the future might be a perspective unique to humans. 5. In the microscopic world of quantum physics, time is no longer continuous. 6. Also in the quantum world, time loses its certainty. An event can simultaneously exist in both the past and the future. We also explored a world without time, discovering that all objects in the universe, such as a cloud or a rock, are simply events in change. Finally, we examined the nature of memory and found that time is a continuous feeling created by our brains. In 1955, when Einstein's close friend passed away, he said something poignant. "He has left this world and gone ahead of me, but it doesn't matter. As a physicist, I know that the distinction between past, present, and future is just a persistent, stubborn illusion." This statement wasn't a theoretical discussion of time, but rather came from Einstein's personal experience with life. It's even deeper than physics itself. Time exists because of us. We are the creators of time.